All right. So we've looked at a titration of a strong acid with a strong base. We've looked at a titration of strong base with a weak acid. Now let's take a look at titrating a weak base with a strong acid. So here's our problem. Let's just start with the base first. What is the pH of zero point 0.1 molar NH3? So this is just like what we did in the previous chapter, where we want to find the pH of just a weak base. So we're going to set up a normal ice table. So that's NH3 is aqueous with water. Mixed with water is in equilibrium with NH4 plus and OH minus. Okay. All right. Aqueous. All right, here we go. So initially, we have 0.1 molar of NH3. We have no concentration of ammonium ion, no concentration of hydroxide. But we know at equilibrium that it's got to go down. The concentration of ammonia has to go down by a certain amount, so 0.1 minus X. The concentration of ammonium ion must go up by X. Concentration of hydroxide ion also must go up by X. Okay. So if we set this up as a Kb expression, all right, Kb would be equal to the concentration of ammonium ion times the concentration of hydroxide ion divided by the concentration of ammonia. Okay. And this is all going to be equal to the Kb value, which for NH3, Kb is equal to 1.8 times 10 to the minus 5th. Okay, so popping in our values. The concentration of ammonia is going to be X. Ammonium ion is X. Concentration of hydroxide ion is also X. The concentration of ammonia is going to be 0.10 minus X. And this is equal to 1.8 times 10 to the minus 5th. So at this point, we can still apply the approximation, which means that X is going to be so small that it's not really going to affect the concentration of ammonia. So that would give us X squared over 0.1 is equal to 1.8 times 10 to the minus 5th. So we want to get X squared by itself. So if we multiply both sides by 0.1, so 1.8 times 10 to the minus 5th times 0.1, that comes out to be, when you multiply the two, 1.8 times 10 to the minus 6th. We take that square root, okay, X is going to be the concentration of hydroxide ion, which is equal to the concentration of ammonium ion. X comes out to be 1.34 times 10 to the minus 3rd. Okay, so we specifically are looking for the pH. We know OH, we know the concentration of hydroxide ion. So if we solve for the POH by taking the negative log of the concentration of hydroxide ion, the POH comes out to be 2.87. So if we solve for pH by subtracting that from 14, that gives us a pH of 11.12. Okay. So that's our initial pH. And so here's our next problem. Let's start adding some acids. So we've got 100 milliliters of 0.1 molar NH3, and then we've got 20 milliliters of 0.1 molar H3O plus. Doesn't matter what the acid is, we know it's a strong acid. All right, so we're going to set this up using the 4-line method. So that means that NH3 and the H3O plus is going to end up being on the right-hand side, and this forms an equilibrium with water, which is going to be on the left-hand side, and ammonium ion, NH4 plus. Okay, so initially we have no ammonium. We need to figure out how many moles of ammonia we have, which is going to be 0.1 times 0.1. So that should give us 0.01 moles of ammonia. And then 0.02 times 0.1 should give us 0.002 moles of NH3, of H3O plus. and I'm looking at the concentration, converting the 20 milliliters to liters, and then multiplying that by the concentration. Okay. All right, so now, if that's what we have at initially, completion, which one runs out first? Well, it's going to be the NH3. So we're going to subtract 0.002 from each of these. So minus 0.002 from H3O, H3O plus, we're going to have no moles of H3O plus left over. For the NH3, we're going to have about 0.008 moles left over. And since we used up all the H3O plus, that means we're also making some NH4 plus, so that's going to give us 0.002 moles of NH4 plus. All right, so we need to find the molarity of this, of the completion. Okay. All right, so we have 100 milliliters of the base, and we have 20 milliliters of the acid, so that's going to be 120 milliliters. So if we take 0.002 moles and divide it by 0.120 liters, or 120 milliliters, that gives us 0.0167 molar. All right. For the NH3, that's going to be 0.008 moles divided by 0.120, or that's going to give us 0.067 molar. And then for NH3, no, 0 molar. All right, so now the equilibrium molarity. We're going to write, for since NH4 plus is on the left-hand side, that's going to be 0.0167 minus X. For NH3, that's going to be 0.067 plus X. And then for NH3 plus X. All right, so we can set this up into, using the Ka expression, but we also need to solve for Ka. We do have a Kb for NH3, and we were given that Kb is 1.8 times 10 to the minus fifth. So we need to convert that to Ka. So we're going to take Kw and divide it by Kb. So 1.0 times 10 to the minus 14th divided by, that was 1.8 times 10 to the minus fifth. So those two together gives us 5.56 times 10 to the minus 10th. All right, so now we can set up a Ka expression. Ka is going to be equal to the concentration of NH3 times the concentration of H3O plus divided by the concentration of NH4 plus. All right. Or concentration of NH3 according at equilibrium would be 0.067 plus X. Concentration of H3O plus is going to be X. And then concentration of ammonium ion is going to be 0.0167 minus X. All right. And this is all equal to 5.56 times 10 to the minus 10th. All right, so we can apply the approximation here and say that whatever X is going to be, because Ka is so incredibly small, 10 to the minus 10th, whatever X comes out to be, it's not going to affect the equilibria concentrations of NH3 and NH4 plus at all. So if we apply the approximation here, the 0.067 plus X will become 0.067. Concentration of H3O plus still is X, and then the concentration of ammonium ion is going to be 0.0167. Okay, and this is equal to 5.56 times 10 to the minus 10th. All right, so we can simplify things a little bit more. Let's say we write a fraction with just the numerator and the denominator, so we get 0.067 divided by 0.0167 times X is equal to 5.56 times 10 to the minus 10. Okay, so if you take 0.067 divided by 0.0167, That's going to give you about 4.012 x is equal to 5.56 times 10 to the minus 10th. So if we divide both sides by 4.012, x should come out, let me get that, 5.56 times 10 to the minus 10th divided by 4.012, x should come out to be about 1.39 times 10 to the minus 10th. All right, so that's going to be the concentration of H3O plus. All right, so we need to solve for pH. Since we have H3O plus already, concentration of H3O plus already, that makes life a lot easier for us. So we just plug the concentration right into the log, into the pH equation. So the pH is equal to the negative log of the concentration of hydronium ion. The pH should come out to be about 9.86. Okay, so think of it this way. We started off at a pH of 11.12. By adding 20 milliliters of a strong acid, the pH has fallen to 9.86. All right, cool. All right, so here's another part. What if, we start with the base again, 100 mils of 0.1 molar NH3, and now we have 50 mils of 0.1 molar H3O plus. Okay, so if that's the case, we're going to start with the same equation that we did before. So we're going to have NH4 plus water is in equilibrium with NH3 and H3O plus. So the initial moles, you've got no ammonium ion. For NH3, that's going to still be 0.01 moles. And for H3O plus, 0.05 times 0.1 is going to give you 0.005 moles. All right, so NH3 is still going to run out first because that's the one in the least amount, but there's definitely more of it. If you notice, this is about the amount of H3O plus is about half the amount of NH3. All right, so completion moles. All right, so at completion, we're going to subtract, we're going to use up all of the H3O plus. Okay, so that's going to give us 0 moles of H3O plus. If we subtract out the all the acid from the base, we're going to have 0.005 moles of base left. And that means we're also making 0.005 moles of ammonium ion. All right, so completion molarity. Okay, we're going to take our 0.005 moles of ammonium ion and divide it by 0.150 liters because we have 150 milliliters now. So that gives us 0.033 molar. And we're going to have the same number for NH3, so that's going to be 0.033 molar as well. And then for H3O plus, because it's 0 moles, it's going to be 0 molarity. So that at equilibrium, we're going to have 0.033 minus X for NH4 plus, 0.033 plus X for NH3, and then plus X for ammonium, for the hydronium ion. So since we're using the same Ka expression as we did above, Ka would be equal to the concentration of ammonia times the concentration of H3O plus divided by the concentration of ammonium ion. And so this is all equal to, that would be equal to the concentration of NH3, which is 0.033 plus X times X for ammonia, for the hydronium ion, divided by 0.033 minus X, and that's the concentration of ammonium ion. And this is equal to 5.56 times 10 to the minus 10th, the Ka number we calculated in the last problem. All right, so if we apply the approximation and say that whatever X is going to come out to be, it's going to be so small that it's not going to change any of these equilibria concentrations except for hydronium ion. that means we should have 0.033 times x divided by 0.033, and that's equal to 5.56 times 10 to the minus 10th. So that means that the numerator and the denominator, we can cancel out a factor of 0.033, so that way that x is equal to 5.56 times 10 to the minus 10th. And this is going to be your concentration of H3O plus. All right. So if we find the pH of this expression, the pH of that hydronium ion, remember the pH is equal to the negative log of H3O plus, the pH is going to be equal to about 9.25. Now, notice how this all canceled out. We were able to cancel out a factor of 0.033 from these, and so that way x was equal to the Ka value. So is there a pattern that we see this in the pH in this problem and some of the others? Yeah, there is definitely a pattern, and here it is. The pH of a reaction, when you're halfway, okay, if the pH is going to be equal to the negative log of the Ka, and whatever that comes out to be, it's going to be the pKa. So at halfway to equivalence, the pH becomes equal to the pKa. All right, and this only works, so we see that if x is really small, we see that the numerator equals the denominator. All right. Okay, so usually in the last two, what we've done is titrate at equivalence. So let's go past equivalence and see what happens. All right, so what is the pH of this new mixture? You've got 100 milliliters of your weak base, and now you got 120 milliliters of 0.1 molar H3O plus. All right, so we're going to start with our same equation. NH4 plus water is in equilibrium with NH3 and H3O plus. All right, so initial, we have 0.01 moles of NH3, no moles of ammonium ion, and for the H3O plus, we're going to have 0.120 times 0.1, so it's going to be 0.012 moles. So this time, we actually have more acid than base. So when we go with completion moles, we're not subtracting the acid this time, we're actually subtracting the base out. So we're going to subtract the base out. So take 0.01 and subtract everything from that, but we're also going to add it, add 0.01 to the NH4 plus. So you're going to get no ammonia left. You're going to have 0.002 moles of acid left, and then you're going to have 0.01 moles of NH4 plus left. So at the completion molarity here, we're going to take 0.01 moles and divide it by 100 plus 120, so the volume, so that's going to give you 220 milliliters, or 0.220 liters. That should give you a concentration of 0.045 molar. For NH3, that concentration is 0 because there's nothing left. And for H3O plus, that concentration is going to be 0.002 moles divided by 0.220 liters, and that's equal to 0.0091. Okay, so at equilibrium, the molarity will be 0.045 minus X for ammonium ion, plus X for NH3, and then 0.0091 plus X for H3O plus. All right, so if we set up our Ka expression, Ka would be equal to the concentration of NH3, which is going to be X this time, times the concentration of H3O plus, which is going to be 0.0091 plus X. divided by the concentration of NH4 plus, which is going to be 0.045 minus X, and that's equal to 5.56 times 10 to the minus 10, the Ka, same Ka that we've been using for this reaction. So if we apply the approximation here and say whatever X is going to be, it's not going to change the concentrations of ammonium ion and hydronium ion, we can say that X, we can rewrite the expression as X for the concentration of NH3 times 0.0091 for the concentration of H3O plus, divided by the concentration of ammonium ion, 0.0045, is equal to 5.56 times 10 to the minus 10th. Okay, so if I rewrite this a little bit and rewrite this, let's put the X by itself. Let me take the numbers and rewrite this expression here. So we got 0.0091 divided by 0.045 times X is equal to 5.56 times 10 to the minus 10th. Okay. If I do that, 0.0091 divided by 0.045, that's going to give you 0.2022x is equal to 5.56 times 10 to the minus 10th. And so if we solve for X is going to be equal to 5.56 divided by 0.2022, 2.7475 if we use sig figs times 10 to the minus 9th. And so that's going to be our concentration of NH3. And if we want to find concentration of hydronium ion, we take our expression, which was 0.0091, plus this number, 2.5 times 10 to the minus 9th, which is really the same as saying 0.0091. So if we find the pH of that, pH is equal to negative log of the concentration of hydronium ion. The pH would be equal to, pH would be negative log of 0.0091. The pH should be about 2.04 for this problem. Okay, so that being said, we can actually draw an approximate pH curve. So keep in mind, let's make a table real quick. Milliliters of acid added, okay, and then pH. So we had no milliliters at the very beginning, and it was all base, and that pH was 11.12. When we added 20 milliliters of acid, that pH was 9.86. When we added 50 milliliters, that pH was 9.25. Oops. And then when we added 120 milliliters, so we overshot, that pH was 2.04. So the curve would look something like this, where pH is going to be on the y-axis, amount of acid is going to be on the x-axis, and so you're going to look at something like this, where it's going to start off, label, we get to the equivalence point, and then it's going to quickly drop off. So right here is your equivalence point. And once we get, so that's the point where the amount of acid is equal to the amount of base. So if we get halfway to that point, so right here, this is where the pH is equal to the pKa, half the equivalence. Okay. All right, so to summarize everything, let's prepare a table to summarize which reaction, which K we use in various cases. Of course, you don't really have to memorize this, just understand how to figure it out. So for the strong acid equation, we had 2 moles of water. That was the autoionization reaction. 2 moles of water breaks down to form H3O plus and OH minus. For the strong base reaction, it's going to be the same thing. 2 moles of water is in equilibrium with H3O plus. and OH. And both of these use Ka. For the weak acid, acid plus water is in equilibrium to form H3O plus base, so that's Ka. For the weak base, that was base plus water is in equilibrium with the conjugate acid plus hydroxide ion, and that's going to be your Kb expression. Now, for the titration, strong acid plus a strong base, we're going to use the autoionization of water again. So 2H2O is in equilibrium with H3O plus and OH minus. And so we'd use Kw for that. For the weak acid, strong base, we're going to use the Kb expression for that. For the strong acid, weak base, that would be base plus H3O plus is going to be in equilibrium with acid plus water. Okay, and we're going to use a Ka expression. And then the weak acid, weak base, you don't have to worry about this. We're actually not going to cover this. Now, that being said, if you go further into chemistry, usually the next level is analytical chemistry. And so you'll actually talk about this and how to do a weak acid, weak base titration in analytical chemistry. But there it is. We have now covered titrations.